Okay, now we're going to talk about looking at your data. This sounds, again, an obvious thing to do, but it's very easy to jump into doing some sort of analysis without actually looking and asking questions about what your data might show. So the first thing you do is you want to eyeball your raw data. Now, that might be actually just scanning log files, but very often you want to visualize that in some way. And there's obviously lots of tools you can use to do that. Particularly, you're going to be looking for things like anomalies. Are there strange cases, outliers? Now, that might be due to some fault in your experiment or your study. It might be that some users are just weird, or where that happens, it might point to some issue that you want to be looking at. Crucially, you're going to ask also, does it match your model? You have some idea of what is supposed to be happening. If you just do lots of calculations, you often assume that certain models and certain things are true of your data. So one of the things you're going to look for is, are those models actually true? But do remember as you do that randomness can be misleading. You will recall this from some of the other exercises that you've done where you look at something, you think you're seeing a pattern, it's not there. So the idea of eyeballing your data is to look for things that might be true or might be problematic. The statistics tell you, actually, is that there, or have you just fooled yourself? The other thing to remember is that data is not truth, and I think this is true of lots of parts of this understanding course. The data itself tells you that things are happening. Understanding what that means is a job that you do in your head, and in particular, generalization is a job you do in your head. As an example of what can go wrong if you don't think about this is Fitz Law data. There's loads of Fitz Law experiments in the HCI literature. They're almost so ubiquitous. You could struggle to find a major HCI conference without something that mentions Fitz Law. When people do Fitz Law analysis, they often jump straight for the index of difficulty. That's, if you recall your sort of HCI 101 course many years ago, it's the log of the distance over the size. So you're trying to hit a target. Here's a target on the screen. You're trying to hit it with your mouse pointer. I'll use my mouse with that. And the question is, how far do you have to go and how big is it? And the log of the ratio, the distance divided by the size, is your index of difficulty. The Fitz Law says that that is the thing that's critical, or found that was the critical value. When people do experiments, they often assume it's the critical value. However, sometimes behaviours are more complex than that. The diagram you can see here is a recreated one, but it basically comes from a paper I looked at some years ago where the experimenters had been looking at adding noise to mouse movements. So you can imagine as you're moving your mouse physically, the little pointer on the screen is jiggling around. Now, there's usually a bit of noise here. So what they were interested in is how important is that noise? If you look at that data, they were expecting it to be. They worked out the index of difficulty. They looked and observed how long people took, and they tried with different target sizes, different mouse movement distances, and different amounts of noise being added. And the graph looked pretty much like this. They averaged each condition. They did lots of trials in each condition. The blue dots are the averages. But it was fairly clear that what you had, they drew the little green line through, the regression line through, but it was very clear there was little series of three blue dots where they'd done one manipulation and they were getting straight lines at one curvature. But also you can see there's a broader curviness to it, that the one at the end is not quite in the line. So there's two things going on. You've got these little jiggly lines and you've also got a bend in it. Crucially, the people doing this experiment never mentioned this in the write-up. Now, actually, if you think a bit about Fitz Law, so this is a bit about the mechanism, again, we'll talk about later, about understanding what's going on. If you add noise to a mouse pointer and you've got a very small target, at the end, the noise is making you jiggle around so much that it becomes quite random whether you actually get there or not. For a big target, it doesn't actually make that much difference and you're just going pointing anyway. And I think that's what caused that curvature. So I think the little lines are when they changed the size, and the big curvature was due to the fact that if you added a lot of noise, things got a bit weird for the small cases. But the crucial thing is not whether they understood why this was happening. That's the second question. There's clearly something going on here that isn't in the model that says it's all explained by index of difficulty. And yet, because they calculated numbers and went straight to it, they didn't look at the data even when they were presenting it in a paper. So one is look at it before you write it up in the paper, but certainly at the point you start to write up in the paper and put those graphs in, look at them and ask if there's something going on that doesn't seem to make sense by your experiment. However, crucially, they drew that line and they actually had statistics for it. So you've done your regression analysis, you've got your significant result for it even, and you think that's the end of the story. So why is it they could have done that statistics, did their regression analysis and thought they'd got it right? This is a curve. This is not a random curve. It's a deterministic curve. It's an x squared curve, but you can see there's a nice curve on this. If you take that x squared curve and fit a line to it using statistical linear regression, you can fit a line, and this is the best fit line you get. If you do that calculation, and you can do it in your stats package, whatever you use yourself, you actually get a correlation coefficient of 0.96, which sounds pretty good. Right? It sounds like you're explaining a lot of the data with the linear line. And if you look at it, actually the line is explaining quite a lot of it. But it's clearly also a curve underneath there. So just because you get a high correlation coefficient, it means there is a trend there, but it doesn't mean the trend is strictly linear. And so in this case, you've got a quadratic curve, and you might, if that was lost in noise, if you imagine if each of those dots on that curve was actually fuzzy noise, you fit your line in, you might not notice it. So again, look at your data. If you believe something is a straight line and it doesn't look like a straight line when you plot it, ask yourself what's going on and why.